Continuing with section 11.1 sequences, we're now going to talk about a specific type of sequence called a geometric sequence. So what is a geometric sequence? Well, geometric sequence is a sequence that has a common ratio between the terms. So the terms increase by a common ratio each time, or decrease by a common ratio each term as the index increases. So our geometric sequences can be expressed in a variety of ways. So if we have just that common ratio, they can be expressed as just r to the n, and that would look like r squared, r cubed, but we could also have a term that starts at 1. So we could have 1, r squared, r cubed. So we could start the index at 1, or we could start the index at 0. So notice these ones, this guy is starting at 1 and this guy is starting at 0. We could also have a constant multiplied by that common ratio. So it could look something like this: a times r squared, a times r cubed. And again, that's starting at 1. And if we started the index at 1, and if we started the index at 0, then our geometric series would look something like this: a times r to the n. But if we start at 0, then our first term is actually a, and then a times r squared, a times r cubed. So we're going to take a look at these geometric sequences, and let's just look real quick before we talk about which ones converge. Let's look at an example. So something of this nature would be an example of a geometric sequence, and this one would be, if we were to think about how we would want to express this guy, we notice that from term to term, and you can always find the common ratio. So if you wanted to find the common ratio, you can take, this would be our first term, or I notice that this has a constant, and so I'm going to actually say that's a sub 0, a sub 1, a sub 2, a sub 3. And if we ever want to find the common ratio, we can take the ratio of the terms to look for that common ratio. So we could say a sub n over the term before it, a sub n minus 1. So if I take negative 5/3 and divide by 5, I get negative 1/3. And then we would check this for a couple other terms too, make sure we have the same common ratio. It won't be geometric if the ratio changes. So then we could say, okay, and notice also that if we were to take 5/9 and divide by negative 5 over, take 5/9 and divide by negative 5/3, we also get negative 1/3. So our common ratio here is definitely negative 1/3. So we find the common, that's one way to find the common ratio. Sometimes we could just look at the terms. We could also just look at these terms and say, well, what is each term being multiplied by to get to the next term? So this is negative 1/3. Sometimes it's more obvious than needing to actually look at those ratios of terms. Negative 1/3, negative 1/3, and so forth. So we can see right there, that's another way to find the common ratio. So if we wanted to express this geometric sequence in its explicit definition, we could say, okay, well, there's also a 5 there, but that's just a constant. So we have 5 times negative 1/3 to the nth. But this is one of those ones where the index is not starting, in this case, unless we wanted to adjust that n. This index is not starting at 1, it's actually starting at 0. So we indicate n equals 0 right here. And that right there is what we call a geometric sequence. Notice here the definition. This is a times r to the n, where n starts at 0. So we have written it explicitly in that definition that we were just defining on the other screen. Okay, so that's a geometric sequence. Which of these sequences converge, and how do they converge, and what do they converge to? So let's take a look a little bit further and take a look at this quick little proof here where we talk about which of these geometric sequences converge. So for what ratios, when you have this common ratio, which ratios converge and which ratios diverge, and how do they diverge when they do diverge? So let's take a look. If r is positive, so if our common ratio is positive, then the limit of the ratio raised to the nth power is going to be infinity if r is greater than 1. It's going to be 0 if r is between 0 and 1. And the limit as we go to infinity is going to be 1 if r is equal to 1. So you could think about those like specific numbers. If you had 5 to the nth power, of course, that goes to infinity. Of course, if you had 1/5 to the nth, that would just get tiny, tiny, tiny as n goes to infinity, so that would approach 0. And if you had 1 to the nth, that's just 1, and so that would be 1. Okay, so that takes care of the cases when r is positive, but what if r is negative? Well, if r is negative, and if in absolute value it's between 0 and 1, meaning it's between 0 and -1, then if we take the absolute value of it, it goes to 0. Therefore, by our previous theorems above, then the limit itself is going to be 0. So r sub n would converge here as well. R to the nth power would converge here too, a sub n. If r is negative and less than 1, then we've got a couple different scenarios. If it actually less than or equal to 1, if it equals 1, then we just have that oscillating switch, -1, +1, -1, +1. So of course that diverges by oscillation. And if r does not equal 1, but is less than -1, then we're going to be oscillating, but oscillating in such a way that we approach positive and negative infinity by the terms, depending on if we're looking at the even or the odd terms, because r sub n in absolute value is going to increase without bound. So as r sub n increases without bound, this guy is going to approach infinity, and then the negative makes it oscillate. -1 to the nth power makes it oscillate. So we can summarize all of that into this statement. A geometric sequence, any of its forms, there's all 4 of the forms we talked about at the top. A geometric sequence is going to converge if the ratio is between -1 and 1, inclusive of 1, and it's going to diverge otherwise. So this is our summary of which geometric sequences converge and which ones diverge. So let's take, and just one more thing, one more definition here. In terms of how they converge or diverge, we actually give some language to this. We give some definitions here. Monotonic and bounded are 2 other definitions that we're going to start using with sequences. And we say that a bounded sequence, a sequence is bounded above or below if it has an upper or lower bound. We can think of those in another word that's sometimes used, or words that are sometimes used. For the lower bound, we think of that as a floor, and an upper bound as a ceiling. So if you have a sequence that never goes below some value and we call it little m, then we call that bounded below. And if you have a sequence that never gets above upper bound, a capital M, then we call that the upper bound or the ceiling of the sequence. And a sequence is defined to be monotone, or approaches something monotonically, is another way to say that, if it's always increasing or always decreasing. So a bounded monotonic sequence would be a sequence that is either increasing or decreasing in such a way that it is bounded, never gets above an upper or a lower bound. So just visually, if we think of our dots here, if we have a sequence, and this, say, is our upper bound, and we have a sequence, and if it's always increasing, never going above that bound, we call this a monotonically bounded sequence. This guy is increasing, always going up, never goes, it doesn't have the up or down, increase, decrease situation. It's always increasing, and it approaches this upper bound.